video is a continuation of the series on current electricity. And previously, we had discussed about the conventional flow of current and as well as the types of current that we come across, the steady, the variable types of current, the current through the solids, liquids, and gaseous medium. Now we'll be learning about the conduction, the process involved in the conduction through metallic conductors that we usually come across in our day-to-day life for availing us with electrical energy. So current conduction in metallic conductors. Now, in case of metallic conductors, what we have is that they comprise, again, I'm considering a very small segment of any given conductor. It's in the form of a cylindrical wire, maybe. And in that case, what we find is that it obviously has a packing of atoms in it, and the closely packed atoms, they have electrons surrounding them. Now the electrons, what happens in case of atom, now this suppose is an atom. I'm giving a view of the atom right now. So in case of an atom, we have the nucleus. So let us say the atom, this is the nucleus, and the electrons around it that I've represented in dots. So these dots that are surrounding that nucleus, these dots or these electrons, in case of conductors, it may happen that the electrons can get sufficient, actually it happens in that way, that the electrons get sufficient energy to just get out of that orbit, and that's the ionization energy, which is quite low in case of the conductors. So with that much amount of energy available at room temperature, the electron comes out, and this now becomes a free electron. However, in case of free electrons, they do not have sufficient amount of energy to exactly move anywhere as per their wish. Okay, so the energy is what determines the uh, the length of freedom that is provided. We can say the amount of freedom that is provided to the electron to move about, because one requires certain energy to move from one place to another, and that is the case with electrons. It has achieved a certain amount of energy, but not that sufficient to move across the entire length of the conductor or even out of its surface. So the electrons, although free, they, now we go back to the diagram inside the conductor. So these electrons, they are free and they have a very little space uh, as per the energy that is available to them. So they move about randomly in very small space around their initial position. So likewise, if I say these are the electrons, free electrons, one atom may give a single free electron or two. So these electrons which are free have a very small space near, very closer to them, that because they do not have sufficient energy to move throughout the entire length of the conductor now, so they just move about, and because they do not have a fixed direction as well, so they move about randomly in one direction or the other. Now we would like to have them move along a certain line so that the current is conducted properly. So what we do is we provide it with a certain potential difference. Now this is a segment of a wire. The segment of the wire is now provided with some field. just as in the case of wire being connected to any voltage source. So when this segment, again I'm drawing a magnified view of that segment. So this segment of the wire, suppose, is connected externally. Externally I am representing it by dotted lines because I have magnified a part of the entire wire. So let me just assume that I have this segment, magnified segment, and now as I have provided it with some potential difference from the source that is down there, the cell that has been provided, or it can be a collection of cells, battery. Okay, so one of the terminals being positive, the other terminal being negative as per the notation goes. So this positive side obviously will have a, or maintain one of the ends. Let me call that end as the end A of the conductor. So this end A of the conductor is maintained. Let me write it as small a because I'll be using the capital A for area of cross section. So this end A of the conductor is maintained at positive potential, while the other end, let me take it as B, is maintained at negative potential. So obviously the positive potential will tend to attract the electrons, the negatively charged electrons, while the negative potential or the negative end will tend to attract the positive ions. However, in this case the positive ions are closely packed, as in case of solids, that is the ionized part of the atom after the electron has been detached from it. So that stays in place. The only thing that is available for conduction, for carrying out the process of conduction, are the electrons. So these electrons, these very electrons that were there in the diagram above, those are now attracted, they tend to get aligned. Now this is a very later view of what happens, and in the process that takes place, these electrons are actually, they tend to rearrange themselves, and as they rearrange themselves they start colliding with one another because of the immense packing that is there in case of atoms. Now you can just consider an example as I consider the case of packing of electrons and atoms. Take for example the case of copper. The copper has a molar mass of 63.5 grams, which constitutes 1 mole of that substance. So 63.5 grams of copper will carry Avogadro's number, that is 6.023 times of 10 to the power 23 number of atoms. Let us suppose that each atom is giving out a single electron. So each atom, that is 6.023 times of 10 to the power 23 for 63.5 grams, just 63.5 grams of copper, that is giving out that many, each atom giving out a single electron. So that many number of electrons are available for conduction from only 63.5 grams. Now obviously the entire length of the wire may be greater than 63.5 grams or whatever the number may be, and accordingly we will have the number of electrons which are available for conduction. So this just gives us the huge amount of ions or charges or electrons, that is to say in this case, that are available for conduction. So the electrons realign themselves, as I said, this is a very later view that we are getting, a very after a long time we can get such an arrangement, because in the process as they align themselves towards the positive charge, they tend to uh, they tend to collide with one another. So in the process as they collide, they now start moving, and because of that collision that takes place, the movement is not that quick. The movement is relatively slow. The movement is of the order of, let us say, 10 to the power minus 4 meters per second. So it's really slow. It is almost 10 to the power minus 3 is millimeters. So some millimeters per second is how the electrons are said to drift through the conductor. So this is what we term as the drift speed. So the drift speed of the electron is of the order of almost 10 to the power minus 4. Now let us take this length that we have considered, let that length be equal to L, and the area, as I had mentioned previously, let that area of cross section be A. So A being the area of cross section, L being the length, and we would like to determine the expression for that drift speed which we have just come across. Now, in order to do that, first of all, let's start with this arrangement that we saw, the first one. In the first case, what we have is that let let us just number out the electrons, although it is just impossible to number them out because they are uncountable. They're just Avogadro's number is just a huge number. You cannot pick one electron or the other just like that. So but we'll just, for our assumption's sake, we can say that u1, let that be the speed at, in this case, under this case, in the first diagram, let us just number it in Roman numerals, that is 1 and this is 2. So in the first case, what we have is that u1 be the speed of one of the electrons that is labeled as 1 right there, and let me change the ink for that in case you might not know. So this is the first electron that we are considering. Let us say this is the second electron, let us say this is the third one, and likewise we can continue up to nth electron, right? So u1 is the speed, with that random motion that they have at that stage. Let u1 be the speed, the magnitude and the velocity as well, and u2 is similarly, changing the ink back again, u2 is the speed or velocity with vector sign for the second electron. U3 is for the third. Now if we tend to obtain an average of all this, then we can just add them up to the n numbers that have been considered as of now, as for the case, and take the average, that is divide the entire thing by the total number of electrons that have been considered, that is n in this case. And what does this come up to? This will be 0. Now why should this be 0? Because they are in random motion, they do not have a net speed or velocity, they do not have a net direction. The net direction as well as the magnitude must cancel out because they do not conduct any form of current at that stage. If I am having a net speed at that stage, that means it has a net velocity, so as to say it has a particular magnitude and particular direction, and for the total number of charges that are available, if they have a particular magnitude as well as direction, that is they are having some value, then obviously we are bound to get some current, right? But as you know, just a conductor laying on the table without any source that has been provided, the potential difference or anything of that sort, any kind of connection not done, then it is just a simple conductor that is lying on the table or in your cupboard. That is not available for conduction at this stage because there is no conduction of current taking place. So obviously with no current you have no net drift speed, and from that we can say that the net uh, the net velocity of all the electrons at that stage has to be equal to 0. Now consider the second case. In the second case, suppose we have provided a potential. Suppose we have provided, obviously we have provided a potential, and that potential has been provided over a given length, and potential per unit length is the gradient of potential. Magnitude wise, I can say that it gives me the electric field that is available across the conductor. Now this electric field that is available across the conductor, that will obviously apply some force, and that force will be equal to the charge on each electron. We can say that the charge of the electron is E being the charge of electron. This is the electrostatics part of it that we have already discussed previously. So this is the charge of the electron, and E is the field applied, which gives the net force that is acting on a single electron, and that has to be equal to the mass of the electron, me. Let us take it as me, that is the mass of electron, and this mass has to be multiplied with certain acceleration that is available to it. So the acceleration is obviously directed along the direction of force, which in turn is directed opposite because of the negative nature of the charge in case of electron. So the force acts on the electron, attracting it. The attraction is represented by the negative sign over there, and the acceleration as well takes place along that line. So now we have the acceleration. Considering the magnitude only, we can say that the acceleration is just E times of E divided by me. This can be the expression for acceleration. Now, having said that, we can now say that the electron will possess a new velocity. So for the first electron numbered as 1 over here, that electron will have a speed, let us say, or acquire a velocity, let us say v1 vector is equal to u1 plus a times of t1, where t1 is the time taken. Now uh, as it is quite evident that we cannot measure the entire time that it takes for the electron to move from the point B to the point A. The entire time will be obviously pretty massive, because the because we know that the drift speed over there that we have, just encircling it, the drift speed that we have with us is in millimeters per second. Obviously for a long conductor it will take a long time for the electron to move from one end to the other end. So it becomes pretty tedious to consider the time, and we are not even considering a single electron. Although we have written it for v1, that is for the first electron, we have a number of electrons to consider up to n, and n can be huge as well, that is Avogadro's number. So this time that we are considering is just the time taken for the electron to collide, or the time taken for the electron by the electron to, or between two successive collisions. Two successive collisions. Two successive collisions mean, well, if I am considering this arrangement, suppose out of that I am considering a small arrangement, many electrons available as well, but I'm considering just three of them. So this first electron, what it does is, this first electron, it moves while realigning itself under the influence of field. It can move in this direction initially, and then collide with this second one, and then after collision it can move to this one, which is a third one, suppose. So this is the first collision, and from 2 to 3 we have the second collision. So successive collision, that is as it moves from 2 to 3, this is the time which has been considered. So between two successive collisions, so the first collision, and from the first as it goes to the second, this this one is the time that we have considered over here between two successive collisions. Then again, for the second, we proceed in a similar way. It would also take a certain amount of time. So v2 is the speed or the velocity acquired by the second electron, and v2 is equal to its initial speed u2 plus a times of t2. Now remember that the acceleration part will be the same for all the electrons that are available, because all the electrons are under the influence of the same field E for the same potential difference applied. The potential difference being the same for all of them, the field will also be the same for all of them for the distribution of charge over that length. So the acceleration and mass of the electron obviously is the same as well in each case. So up to the nth term, we can say this velocity of the nth electron will be un plus a tn. Now the drift speed as we define it is we can take it as vd, is what we know as drift speed. So this is the drift speed or velocity, we can say. Magnitude wise it is speed, or vectorially it is the velocity. Obviously we are considering the vector addition, so mostly it is termed as drift velocity with the vector above it. So vd is equal to the average of all of these final velocities that is acquired by each and every electron that we have considered. So v1 added to v2 up until vn whole divided by n. So we can write those terms explicitly, that is u1 vector plus a t1 plus u2 for the second case, u2 vector plus a t2 up to the nth term. We have un vector plus a tn whole divided by the total number of electrons, that is n in this case. So now moving over to the second page, now we have a certain number of electrons available to us which are conducting, and we have a net speed. We have to obtain a net speed for it, or net velocity expression. So vd, if we get back to the initial page, we have vd is equal to u1 u2 un terms. They can be taken separately. So you have the first term of each set of terms, that is u1 plus u2 taken up to un, that entire thing divided by n as in the previous case, plus from the second term that is with us, in this second term we have at1 at2 atn up to atn. So we can take that and divide the entire thing with n, as a is the common term in each case. So we have just t1 t2 taken up to tn divided by n. Now this first thing, as you know, goes to 0, because we had just discussed that, because this was the condition. This was the condition in that case, where we had this entire thing to be equal to 0, and we are using the same thing over here. So that, as that goes to 0, the second term remains, and in case of the second term what we have is A, and this entire thing that has been taken as T1 plus T2, that is just denoted with a symbol that is tau, and here tau is just the relaxation time. We define it, the relaxation time. What exactly is that? uh, we know that T1, T2, T3, Tn are the time between two successive collision. The average of that is what we term as the relaxation time. So average of all the successive collisions taken is the relaxation time. Now initially, if you remember, we had an expression for the acceleration that was right there at the somewhere in the middle, this thing. This one. In that, we have A equals E times of E divided by ME. So this thing that we have just obtained, that is equal to E times of E divided by ME. And because we are notifying this thing vectorially, so we have this to be a vector. The charge of the electron must be considered, considering the direction being opposite to that of the field, direction of motion, and tau remains as such, that is the relaxation time. So now we have an expression for the drift speed, that we drift velocity in case of vectorial representation. So this is just E times of E divided by ME times of tau. Again, we know that E is equal to V by D, so this is E V divided by ME times of L times of tau. The negative sign gives the direction of the flow of electron, which is exactly opposite to that of the field, or the potential gradient that is going across the given segment. So there we have it. Now the charge of the electron is of the order of, say, 10 to the power minus 19. Mass is 10 to the power minus 31. So that gives me 10 to the power plus 12. The length is obviously as chosen. Let us take it as a millimeter or a meter length, right? The voltage is an average voltage of, say, 2 to 3 volts or even 10 volts. So of the order of 10 to the power 1. So all that taken into consideration, you have this entire segment that we entire section of the expression that we have. It's roughly equal to 10 to the power say plus 12, which is quite huge. But as we know, the drift speed is very less. Drift speed is of the order of 10 to the power minus 4. So that means that this relaxation time term, that must be really small, that is 10 to the power minus 16 seconds. And that is the whole reason why we are taking an average of it, because we cannot really determine that small a time. uh, in the first place, we cannot determine the flow of electron individually. We cannot see them. They cannot be determined individually. So even the microscope won't help to observe an electron, because they're really small and lighter. Even photons will bounce them off their track, which is the case that we have learned in Heisenberg's uncertainty principle. So this entire thing gives us an idea about the time of collision, which is very short, because they are randomly in motion and they are very closely packed, and that is why they collide at just like that, 10 to the minus 16. By the time you start counting, it's over. So this gives us an idea about the drift speed. Now this drift speed being very small, how do you really uh, observe the lights or the electric devices, electrical devices, appliances, just like your ceiling fan, the light bulbs? They start operating instantly as you switch them on. So how do you expect that to happen with such a small speed? Well, the answer is that although the speed of the electrons is small, but the electrical energy is activated once you switch a circuit on. Once you switch a circuit on, there's a whole range of electron in the wire connecting the terminal where you have the point or the terminal where you have the switch and the electrical appliance. So it's a complete circuit. So let us say this is a bulb that we have over here, right? And the bulb is connected to a switch. Now as this switch is closed, that means it is on. The obviously the I have forgotten about the potential difference provided. So this is the potential difference provided here. Now as it is switched on, initially as it was open, the switch was closed, so the system wasn't operating. Now the system has started operating. The bulb glows instantly because the potential that is provided over there, that gets activated. So now you have a net potential energy and whole range of electrons throughout this entire length of the conductor. Those charges, as you have learnt in the previous case in electrostatics, those charges, those electrons under the influence of field provide you what we call as the potential energy. So this potential energy is available throughout the conductor, even if the electrons are moving sluggishly, but still you have the entire electrical energy activated for the range of for the entire range of the conducting wire. And so what you achieve is the electrical energy that is quite expected. In the next video we'll be just moving along with this expression of drift speed, and from that we can obtain a relation between the current that is flowing in the circuit with respect with the drift speed, the relation between them, as well as the Ohm's law that is associated with it. Till then, thank you.